Good morning, dear students. Today we have the seventh practical lesson. It is the first lesson in a new module, differential and integral calculus of function of several variables. And today we will differentiate functions of several variables. Okay, let me remind you some formulas. So about a total differential function. So it is the sum of uh, uh, partial derivatives multiplied by dxi. So each of these variables. And the second differential is the following formula. So sum of second derivatives multiplied by dxi dxj. Here is the formula of total derivative of function. So when it is a composite function that depends not only on t variable but on functions that also depend on variable t. Here is the derivative of composite function formula. We will use them in our tasks. So we will return to them later. Now I just reminded you them a little bit. First of all, before starting differentiating, let's just remember some information about functions of several variables. So the first task is to find the domain of the following functions. So 1a, we have the following function, logarithm of 4 minus x square minus 4y square. So we need to define the domain. We know that argument of the logarithm is always positive. So it cannot be 0, it can be only greater than 0. So now let's modify it a little bit to understand the domain better. So let's move x squared, so let's move variables to the right part. And now let's turn over this inequality. You already should see that here something like a curve of the second order. So let's divide by 4. And what do we have? So it is similar to the equation of the ellipse. But here we have the inequality. So what does it mean? So the domain of this function is a region that is bounded by the ellipse given by this equation, but not the ellipse itself, so excluding ellipse. Let me plot this region. So what do we have? X square by 4 plus y square is less than 1. So we have such elliptic, the region that is bounded by the ellipse, but we can see that ellipse is excluded because the logarithm cannot be 0. So any questions about this exercise?
No.
No questions.
Okay, moving to part B. So we have the following function that depends on 3 variables. So u equals minus x square minus y square plus 2z. What can we say about this function, about this expression. So we know that the expression under square root is non-negative. So it can be equal to 0, and it, it can be greater than 0. So here we have not, here we have a region that is bounded by a surface. So let we move x and y to the right part, and we will see something interesting. So actually we can, so we have inequality that is similar to equation over paraboloid, elliptic paraboloid. What does it mean? That the region of that the domain of function u is elliptic paraboloid and all points that are above it. Yeah, let me also maybe divide it by 2 as well. So that will be that equals x square over 2 and y square over 2. So now let me plot this surface. So okay, if I plot the paraboloid, so x square by 2 and y square over 2. So I have such a paraboloid. Let me make it transparent. So we can see such surface, but if I write such inequality, I will receive the following. So all points that are on the paraboloid and all points above it. This is actually the region of the function u. So any questions about this exercise? Okay,
No questions.
So moving next. The next task is to find level lines of a function. So we have the following function z equals 2x plus y. So actually this is a plane, and what do level lines of the function mean? So these are lines on which a function has the same value. So they can be defined, so they're defined by the following equation: 2x plus y equals c. So c is a parameter. So actually we found the level lines, and now let's plot them. So I can add slider, for example, and I can modify it. And so which value of c we will assign, it actually will be the line, a level line of the function. I also can plot several graphs. So all these straight lines are level lines of the function. Any questions about this exercise?
No questions.
So this is the line on which function equals -2, on this -1, and so on. Okay, moving next. Now we have a three-dimensional case. So we need to find the level surface of the function of the following function: x square u equals x square plus y square plus z square. So for function of two variables, we find the level lines, and for function of three and more variables level surfaces. As well, they are found. They can be found from the following equation. So these are surfaces for which value function equals c. So the same. And as we can see, this equation is similar to equation of the sphere. So yeah, this is by the way, this is really the equation of the sphere. So let's plot this surface, and I can also modify the slider. Yeah, let's plot also multiple graphs. We can do it. So multiple spheres on this graph. Yeah, here they are even cut out a little bit, so we can look into them. Any questions about this exercise? So we have
No.
concentric spheres. No questions, right? Okay, let's move next. And finally, we are calculating partial derivatives of functions. So the first, for A, we have a polynomial function z equals x in power of 5 plus y in power of 5 minus 5 x cube y cube. So let me remind you how to find partial derivatives. When we differentiate by one variable, so for example for x, other variables y in this case, so we just suppose them to be constants. And what does happen with constants? They are differentiated to 0. So when we differentiate by x, what we have 5x in power of 4 minus 15x square y cube. And now differentiating by y. So we have 5y in power of 4 minus 15x cube y square. Any questions about this exercise? Okay, no questions. So moving to the next function, z equals xy over square root of x square plus y square. Let's differentiate. Dz by dx equals, so reminding you the rule of differentiating the fraction. So first of all, let's write the square of the denominator here. And now, so x, so y multiplied by this function plus plus x y divided by 2 these square roots and by 2x. Let's simplify it a little bit. So I will write square here, and I also can cancel 2. We also can move to the common denominator, but let me know. Oh, stop, minus, sorry. By the way, yeah, we can move to the common denominator, and the expression should be simplified. So let me multiply both the numerator and denominator by this square root. And what I will receive? So here I will have y by this expression minus x square y. Yeah, so it will be simplified. So what can we see that this so x square y will be cancelled, and we will have y cube divided by this expression. And now let's find dz by dy. So again, the same with denominator. Now, x multiplied by the square root, minus here, and minus, so to these expressions, so xy here, and by 2y, so removing 2, xy square, and now doing the same, so again multiplying by square root, both parts of the fraction. And what we will receive? So again, xy square will be eliminated, and in the numerator remains only x cubed. So any questions about this exercise? No
No.
question. Okay, let's move next. For C, the following function of three variables, sine of x in power of y z. So let's differentiate du by dx. So when we differentiate by x, we have a composition of sine and so composition of trigonometric and power function. So let's first of all differentiate the outer function. So yz multiplied by sine of x and in power of yz minus 1 and multiplied by cosine of x. Now, du by dy equals, so here now we have exponential function, because so for y it is exponential function. And what do we have? So yeah, z is a constant multiplier in this case. So z multiplied by sine of x in power of yz, and also multiplied by logarithm of sine of x. Now du by dz, so actually it is analogical. Y multiplied by sine of x in power of yz and multiplied by logarithm of sine of x. Any questions about this exercise? Okay, so no questions. Moving next. Now we are finding total differentials of functions. So 5a, we have the following function z equals arc sine of x over y. So first of all, finding partial derivatives. So the derivative of arcsine is the following. So 1 minus x square by y square and multiplied by 1 over y. Now, yeah, and let's also simplify it a little bit. So I can move I can move y under the square root, and I will receive the simplified expression. So y square minus x square. So 1 over this square root. Now differentiating by y. So again, I have the following multiplier, and now for y, so when differentiating by y, I have the following expression, x over y square. So let's also move y under the brackets, under the square root, and I will receive the following. So I have such expression. So found partial derivatives, and now let's calculate, let's find the total or differential. It can be found by the following formula. So the total differential is the following. So it's done. Any questions?
So we don't need to find dx and dy, not a partial but full derivative. Yes.
Why we found both partial, yeah. So what you mean total derivative? It is related to some composite function. Do you mean this one? No, we find the total differential. So this is another case you understand from another task.
Okay. Thank you.
More questions? Okay, let's do more practice. One more exercise for finding total differentials. So we have the following function. So now let's find derivatives. So du by dx equals yz x in power over yz minus 1. Du by dy equals z x in power over yz by logarithm of x, and du by dz equals y x in power of yz by logarithm of x. Now finding the total differential. So multiplying it. So the total differential is found. Any questions about this exercise?
No.
Okay, if no questions, let's move next. Yeah, and here is the task for the total derivative. So I will explain it. I will explain you what does it mean. So we have the following function z equals e in power of x minus 2y, and function x is a function sine of t, and y equals t cubed. So x and y are functions as well. So we need to find the total derivative. So it just means so total derivative of the function is it's a function that is that depends on another functions. So similar to composite function, but actually f so z in this case is a function that depends on t. So let's use this formula. So partial derivative of so if we differentiate z by t, we will receive 0 because t is not, so we don't have t here. Then dz by dx equals this exponent. So nothing changes. dz by dy equals minus 2. Minus 2 e in power of x minus 2y. Now differentiating x and y. Here we have straight letters d because x and y depend on one variable. So the derivative of x by t is cosine of t, and derivative of y by t equals 3t square. So now let's use this formula. Let's multiply everything that we have, that we need here. So dz by dt equals e in power of x minus 2y multiplied by cosine of t minus 2 exponent over x minus 2y multiplied by 3t square. And now we will simplify this expression, and also so reduce it only to one variable. So we will simplify everything. So let's move e in power of x minus 2y out of brackets. So in the brackets I will have cosine of t minus 6t square. And now let's substitute x and y with these functions. So x in power of sine of t minus 2t cube. So we found the total derivative of a function of one variable. So now do you understand the difference between definitions of total differential and total derivatives? That they don't really mean they don't literally mean the same.
Yes.
So any questions about this exercise? Okay, if no questions, let's move next. So task number 7. So again, here we will find total derivative of the function. So z equals arctangents of xy, and y equals e in power of x. So again, we will use formula of total derivative. But here we have only one function that depends on variable x. So firstly, we need to find partial derivative of z by variable x. So dz by dx equals 1 over 1 plus x square y square multiplied by y. So actually we have so y over 1 plus x square y square. Now differentiating by y. So again, we have the same outer derivative of the outer function, but now it's multiplied by x. And now differentiating y by x, of course, we see that we have e in power of x, so nothing will change. And now we have everything to find the total derivative. So dz by dx equals so firstly dz by dx plus this expression multiplied by e in power of x. So now it's okay. Now that we move everything to the common denominator, so what do we have? Y plus x by e in power of x. And let's substitute y with e in power of x. So what I have here, e in power of x, and let's move it out of brackets, by 1 plus x. And in the denominator, 1 plus x square e in power of 2x. And it's done. Any questions about this exercise? Okay. No questions. So moving next to exercise number 8. Now we have to find derivatives of composite function. So we have the following function: z equals x square y minus x y square, and x and y are also functions of two variables. X equals u by cosine of v, and y equals u by sine of v. So let's use the formula of the composite function. So how to use this formula? So dz by du equals, so I need to find the derivative. So I need to find derivatives of function z by these inner variables y and u. So if I want to find dz by du, I need to firstly differentiate it by x, by outer function, and then multiply by the derivative of this outer function, and plus the same with y, differentiated by u. Okay, so finding all these derivatives and putting everything together. So first of all, let's differentiate z by x and y. So dz by dx equals 2x y minus y square. So differentiating z by y, we have x squared minus 2xy. Now differentiating y and x and y by u and v. So dx by du equals cosine of v. Dx by dv equals minus u sine of v. Now analogically to y, so dy by du equals sine of v, and dy by dv equals u cosine of v. And now let's put everything together. So dz by du equals, so dz by dx, so this expression multiplied by cosine of v, and plus this expression multiplied by sine of v. So found. Then dz by dv. So again, so we have, so inner functions are the same. So derivatives of outer functions are the same remaining. So minus this u sine of v plus this expression by u cosine of v. We also can move, so ideal variant is to move to the so absolutely to variables u and v, but it will consume a lot of time to reduce these expressions. Yeah, so in this example, you will have the final result when these expressions are reduced, but now let's not spend time for arithmetics. And now let's move next to the task number 9, or you have some questions maybe.
No questions.
Okay, if no questions, let's move to the exercise 9. 9a. So we have the following functions. So a function of one variable y that depends on x. But we will, so you know how to find it. Actually, we need to differentiate both parts of the equation and then solve this equation with respect to y prime. But with using functions, so differential calculus of functions of multiple variables, we can solve it in another way. Let's write this expression that it on the left side as a function that depends on x and y. So the derivative of explicit function in this case can be found by the following formula. So partial derivative of, so minus partial derivative of x by variable x, or function of minus derivative of f by variable x divided by partial derivative of f by variable y. So now let's find these partial derivatives. So df by dx equals e in power of y plus y by e in power of x minus y e in power of xy. And then df by dy. So equals x e in power of y plus e in power of x minus x by e in power of xy. And now let's just differentiate it. Oh, now let's divide everything. So it looks like this. Unfortunately, these expressions cannot be simplified. Yeah, so here is a mistake in this exercise. Yeah, I just was thinking that these parts are equal, so I didn't notice that the so different power of the exponent. So and here the same. So this answer is correct. Any questions about this exercise?
Can you scroll up a bit?
Yes.
No questions, thank you.
Okay, one more exercise, 9. Okay, so 9b. We have the following implicit function, xy minus logarithm of y equals a. So again, let's, I raised formulas, so let's let we remain it. So, okay, so it will be remained. So xy minus logarithm of y equals a. So we have the following expression, xy minus, so f from xy equals xy minus logarithm of y minus a. And now differentiating f by x and y. So df by dx equals y. Df by dy equals x minus 1 over y. And now let's differentiate. Now let's divide this. So we have the following formula. So the following expression, let's multiply denominator by -1. So we will have 1 over y minus x. And then let's multiply the numerator and denominator by y. And this is the final answer. Any questions about this exercise? Okay, no questions. So let's do one more exercise, task number 10, and then we will have a break. So let's do the logical point. Let's complete it. So now we have to find the partial derivatives of implicit function of several variables. So the function is the following: x squared minus 2y squared plus z squared minus 4x plus 2z minus 5 equals 0. So we have the following expression, a function that depends on function f that depends on x, y, z. So this left part And we will find derivatives, so partial derivatives analogically. So dz by dx will be equal minus df by dx over df by dz. And for variable, for the partial derivative by y, analogically. So now let's find all these total derivatives. So df by dx will be equal to x minus 4. df by dy equals minus 4y minus 4y. And df by dz equals 2z plus 2. So now finding these derivatives. So df by dx here, so 2x plus 4 by 2z plus 2. Let's reduce it by 2. So x minus 2 over z plus 1. And yeah, don't lose signs. And now let's multiply also the numerator by minus 1, so we will have 2 minus x. And here, for this part, so minus 4y by 2z plus 2. So minus it will be eliminated, and also we can reduce by 2. So 2y, damn it. So 2y by z plus 1. And that's it. So found the partial derivatives of implicitly given function. Any questions about this exercise?
No.
Okay, if no questions, let's have a break for 5 minutes and then we will continue finding derivatives of the higher order. Let's continue. So now we will find derivatives of so higher derivatives of functions of the several variables, and now we need to verify that mixed derivatives of firstly by dx and by dy equals d to u by dy dx. So that order of differentiating is not important. We have such polynomial function. And first of all, let's find first derivatives. So dz by dx equals 12x square plus 6xy plus 3y square, and that's it. Dz by dy equals 3x square plus 6xy minus 3y square. Now let's find the mixed derivatives. So d2z by dx dy. So here is the order of differentiation. So now we differentiate the first derivative by y. So d by dy and this expression. So what do we have? 6x plus 6y. Now finding in another order. So d to z by dy dx, and now we differentiate the the first derivative by y, then we differentiate by x. And what do we have here? So 6x plus 6y. So we see that these mixed derivatives are equal. So d to z equals, so by dx dy equals d to z by dy dx. And the final answer will be what was required to check. So in such tasks, you must also write the conclusion. So not only calculate, but write the conclusion that you see that really, so it is true. Any questions about this exercise?
Can scroll up a bit?
Yes.
Thank you, no questions.
Okay, maybe anybody else has questions? Okay, let's move next. So to exercise number 12. And now we have to find the clear derivative of the second order. So first of all, let's write down a function u. U equals x sine xy plus y cosine of xy. So finding the first derivative by x, so du by dx equals, so here is a product of functions. So sine of xy plus xy cosine over xy and minus y square cosine of xy. So found the first derivative, and now finding the second derivative, d2u by dx square. So we need to differentiate the following expression. So y cosine over xy, so differentiated, and now let's move our y out of brackets, plus y, so cosine of xy, and minus xy sine over xy. So differentiated this expression and moved out of y out of brackets, just not to confuse us. And minus and plus y cube by cosine of xy. Now let's see if we can simplify this expression somehow. So let's expand the brackets. Minus xy square sine over xy and plus this expression. So yeah, we can write it as a sum. So 2y cosine of xy. And actually that's it. Yeah, we can also move y out of brackets, but we really don't need to simplify somehow this expression because we don't need to do anything else. Any questions about this exercise?
No.
Okay, if no questions, let's find the second differential of the function. So task number 13, so total differential of the second order. U equals e in power of xy so finding first derivatives first of all, so du by dx equals ye in power of xy. Then du by dy equals x by e in power of xy. Now let's find second derivatives, and I recommend you first of all finding mixed derivatives, just to and if you see that mixed derivatives are equal, it means that first derivatives are calculated correctly. So differentiating this expression, so differentiating the first derivative by so this derivative by y. So it equals e in power of xy plus x y e in power of xy. Now let's calculate the second mixed derivative in other order. So dy dx. So differentiating this expression. So e in power of xy plus xy e in power of xy. So these derivatives are equal, so it means that first derivatives are calculated correctly. So now finding clear derivatives. So d to u by d x twice. So it will be equal y square e in power of xy. And d to u by d y twice equals x square e in power of xy. And now let's find the second differential. So by the following formula, let me remind it for you. And the partial derivative by y. So this is the formula of the total differential of the second order. So now putting everything together. So this expression by dx twice plus 2 these expressions by dx dy and plus this expression by dy twice. And finally, so found the second differential. Any questions about this exercise? Okay, if no questions, let's move next. Exercise number 14. Yeah, and it is actually the last exercise for today. So we need to check that function z equals y square over 3x plus arc sine of xy. So that we need to check if this function satisfies the following differential equations. So how to do it? We just need to substitute it into the equation. So we will have to find partial derivatives and substitute them. So writing down this differential equation. So finding first derivatives, partial derivatives. So differentiating by x. So what do we have? Minus y square over 3x square plus 1 over square root of 1 plus 1 minus x square y square and multiplied by y. Okay, let's write like this for now. Then dz by dy equals 2y over 3x plus so outer derivative of arc sine by x. So now let's substitute these derivatives into the equation. So x squared multiplied by this derivative minus xy multiplied by this derivative and plus y squared. Okay, let's expand all these brackets. Expanding first brackets, minus 1 over 3 y squared plus x square y over the square root minus. So done with these brackets. Now expanding these brackets minus. So 2 over 3 y square. So x is eliminated and y square remains. And minus this square, so minus x square y by this square root and plus y square. So what can we see now? So now we can cancel these add-ons, these fractions, and here we see that so minus 1 minus y square plus y square, so equals 0. So finally, yeah, function z satisfies the differential equations. And of course, let's write down the conclusion. So that's it. So it's done. Any questions about this exercise? About the whole lesson, about previous lessons, home tasks?
We already can do the module test number 1.
Yeah, it should be unlocked already, if I'm not mistaken. If it's locked, let me know. Or you even can check it now. So if you have the access, it means that you can start working.
Yes, it's unlocked.
Okay, so you can complete it. So unlocked. Oh,
Yes, unlocked.
okay. Great. So more questions?
Can you see Google Chat? I have sent a question to you.
Thank you for reminding. Yeah, sometimes I'm not often can see this.
It's not a big question, but for to be sure that
Yes, okay, I will see it now. So yeah, after the lesson, more questions. Okay, if no questions, have a nice day. So we have done everything that we planned today. So goodbye, stay safe. Thank you for
Goodbye.
your attention.
Goodbye.
Thank you. Bye.
have a nice day too.
Thanks.